So, the first algorithm, k-means clustering. The simplest, clustering algorithm there is, probably the first one you'll use for any problem. This is like the nearest neighbor or the naive Bayes of clustering. Okay? How many people here have actually heard of k-means clustering? Okay, that's actually a few of you. Okay? So, what is k-means clustering? It's a very simple idea. You can program it in, half an hour, right? First of all, you just pick random examples as your initial means, right? So k-means, or k-means clustering, at least in its basic form, is an algorithm for classifying for clustering numeric examples, right? So you're in Rn, right? And my goal is to find k-means, right? So each cluster is going to be represented by a mean of some set of the points, okay? So I'm looking for k-means. Okay, so what do? How does the algorithm work? I pick, let's say, some set of random examples as initial means, or some other criterion that you might have, right? I need to pick initial positions for my means, okay? And then I just alternate between the following two things. I assign each example to the nearest mean, okay? So let's say that my examples were here in this room, right? And I say like my initial, mean is one here and one is over there, right? So if there's an example over here, it's closest to this mean than to that mean, so it gets assigned here, okay? So basically, I divide my examples into k subsets. Each subset is the examples that are, in the Voronoi cell of one of the means. Okay? Simple idea. And then what you do, right, is you compute the new mean as the average of the examples that were assigned to it. Right? Now there's this mean here in this argument, it's winning these examples, right? But maybe it's a little off from their mean, so what I need to do is compute their mean and I'll move my new mean to that. Okay? Now, of course, since my mean has moved, maybe now it's going to win some new examples and lose some old ones, so I need to do this again. And when finally I converge, meaning that on two successive iterations I get the same mean, I'm done. Okay? Simple algorithm. Okay? And the running time is actually not too bad, right? The running time of this is just order of k, right, which is the number of means, times the number of examples, right? Because I need to compare each example with each mean, right? Times the number of dimensions, right? Because computing in distance, has cost number of dimensions. Times my number of iterations, which I don't know what it's going to be, but let's hope that it's not too large, right? Okay, so, this is not great, but it's not too bad either, right? There is one question here that immediately arises, which is what? Is there a question that comes to your mind apropos of this algorithm?
How many k?
Mm-hmm. Oh, how do you pick k? Yeah, exactly. How do you pick k? Right? Did somebody tell you what the k was? Well, yeah, on a good day, somebody will tell you. Actually, here's the interesting thing. For example, marketers, and actually oftentimes people will tell you what k is. Not because it's the real k in the data, but because it's the k that they want. Like say, I know someone working with marketers at a company that I shall not name, where they told them that they wanted 7 clusters. And they said, but I've really clustered this well, and there's, I don't remember, like 20-something, like, we do not care about your 20-something clusters, we want 7. And it's easy to smile at this, but the thing is that if they have 7 clusters, they can say develop 7 different marketing strategies. They are not going to develop 20 different market strategies, right? So, maybe it makes sense. On the other hand, if your question is like how many clusters are there really in the data, right? Now we get this from, well, what does it mean, really in the data, right? There's no clear answer to this. Okay? So what people often do is you can try different, case, right? And then you look at the results, and once you have a result that you're happy with, you take that. You can say oh no, this thing is really singling out very small clusters, not good. Or, this is really glomming together things that shouldn't be glommed, I need to refine it, right? So you need to play with k. This can be done automatically, right? But the thing is that if you do this fully automatically, then this k becomes n. Okay? Because you need to try from 1 to n clusters. And then, this whole thing becomes n squared, and now this does not scale, for sure. Okay? There are many algorithms, a lot of, data mining work has gone into making clustering algorithms scale up, right? We're not going to look at that, but they certainly exist. Okay? So this is k-means. Easy algorithm, widely used, probably one of the first things you should try. Questions about k-means?
Is there any limitation on distance between any two?
Oh yeah, so how do you measure distance is, as I said, you can pick the measure, right? Usually k-means use it with something like, Euclidean distance, or weighted Euclidean distance, or Euclidean distance where you've normalized the variables to all be between 0 and 1, right? So.
My question was if you keep changing the mean, will that...
Oh, I heard this. If you keep changing the mean, yeah, then what?
Can the distance between any 2 points become larger than when we do
Become larger than what? Sorry.
when we're clustering and you're keeping moving the mean, then the distance between any 2 points, any 2 extreme points might get larger. That's fine, I guess.
Sorry, can you speak louder? Larger than what?
Like, say we want to cluster all these points into one, and other set of points into another clusters.
Mm-hmm.
But if we keep changing the mean, there might be an option like it keeps growing.
The distance between.
The output is just the clusters of points. Is that what you were saying? That you don't actually, what the output is not a bunch of clusters. It's actually just the single points that represent each mean.
Well, you can return both, right? So when I'm done, right, I know two things. I know where my means are, right? This is usually what people ask first, right? Where are my means? Or there's one mean here and there's one mean there. But you can also ask in like for each object, right? What mean was it assigned to, right? And then you can return both of those things. Right, and remember, k-means is a greedy algorithm, right? So usually what is going to happen is that the distances are going to, on average, are going to keep shrinking, right? So you'll get better and better clusterings if you measure that by, the average distance between the points and their centroids. Is that what you were asking?
Yeah, that's fine.
Okay, good. Now, we are not done, right? K-means is our first clustering algorithm. It's not our last one, right? So the next question to ask is, when is this going to work versus when is this not going to work, right? First of all, as with a lot of these algorithms, you probably want to try a number of different random initializations because one of them might just, behave badly, right? But even beyond that, there's a whole bunch of situations where k-means is very likely to misbehave. In fact, the set of conditions where k-mean will usually give a good result if, properly taken care of is quite narrow. So in particular, k-means needs all the following conditions to work well, and we're going to see the reason for each one of them. It works well if the clusters are roughly spherical, not very elongated, say, and they are well separated. There's one cluster over here and one over there. They're not kind of like all of intermingled, and you can't tell very well where one ends and the other one begins. It works well if the clusters are of similar volumes. K-means often runs into trouble if one cluster is all bunched up here and then another one is very widely distributed. And finally, it works well if the clusters have similar numbers of points. Notice that this is different from volume, right? Because you could have larger or smaller, higher or lower density, right? But if one cluster has, 10 data points, another one has, 1 million, this is going to be trouble. Okay? So first of all, let's see why, these things are the case, right? And then let's see what we can do about them, right? So here's an example to illustrate why clusters need to be spherical, right? Let's suppose that, and I'm going to use ellipses to represent my clusters, right? Let's suppose that these were my two clusters. Right, so picture a bunch of data points in this cluster and a bunch of data points in this one, right? So these clusters are very much not spherical, and this happens a lot in practice. And again, remember, it's not just a matter of rescaling the data because the clusters, this thing could be in any direction, right? So just rescaling thing doesn't necessarily solve this problem, right? So what do you think k-means is going to do here, right? How is it going to fail?
But we're going to cluster them across both.
Exactly. K-means is going to say oh, there's a cluster here and there's a cluster here, right? And this, if you look at the world through the eyes of k-means, this is very natural, right? Because, you're using Euclidean distance, right? And the truth is that, this guy, right? This guy here is a lot farther from this guy than it is from this one, right? So guess what? This is what k-means is going to do. Disaster. Okay? Everybody got this? So, disaster number 1. Disaster number 2, the clusters need to be well separated. Right? Why do you think things are going to misbehave? So the clusters being well separated means, there's one cluster over here, and there's another cluster over there. Of course, I'm exaggerating, right? But in this case, clustering is not too hard, right? Because it's kind of obvious what the clusters are, right? The hard case is when you have something like the following, right? Here's my, blue cluster, and here's my red cluster. It's actually not too hard to see why k-means might have trouble with this, right? Because, even you and I might have trouble looking at this and, deciding where the clusters are, right? In this case, I kindly drew the boundaries, but if this was a bunch of points, right? Nevertheless, it might be, this happens a lot, right? There are generally different clusters there. And in fact, when we look at the better methods for clustering, we will see, how that comes about and how we can detect it. But if you don't have a lot of data points and things are overlapping a lot, it's very hard to tell exactly where one cluster ends and the other one begins. Okay? So this is problem number 2. Problem number 3, right, is a slightly more insidious one. It's that the clusters had better be of similar volumes, right? So suppose that, my blue cluster was like this, let's suppose that my red cluster was like this, and my blue cluster was like this. Right? Blue and red are marketing names, right? But the content doesn't change, right? So why might this be a problem for k-means clustering? What do you think might happen here?
Some of the blue examples are nearer to red, so it might get included in red.
Yeah, exactly. So number 1, right, you might get clusters like this, right? I get a cluster that actually captures some of this chunk, right? And then, the blue cluster is the other one, right? Because that cluster just looks like a few more data points off of the big cluster that's in the blue, right? So this is one thing that can happen, right? But in fact, things actually here could go bad from the start. You know why? Right? It's one thing to say like, your clusters are going to converge to the wrong thing, right? But this actually can be worse. The clusters could start off in the wrong place and never recover. Why might the clusters start off in the wrong place here? Right? Remember that what I do is I first, pick my, let's say I'm doing 2 means clustering, right? So I'm going to pick 2 data points at random to be my, cluster mothers, right? So where are those points going to come from?
The big blue block.
Well, actually, I lied, right? This is the 4th problem. Right? This was testing the distinction between those 2, right? So everything that I said about the 3rd problem, or that you guys said about the 3rd problem, was true, right? But this is actually a problem with the 4th. This is actually the 4th problem, right? If clusters have very different numbers of points, right? Notice that the problem with volume, right, is that again, when I'm clustering things by distance, right? Well, I'm easily led astray, right? But when clusters have similar numbers of points, let's suppose that the clusters are of similar volumes, but they have different numbers of points, right? Another problem comes in that it's a very lucky day where I actually choose one centroid from one cluster and one centroid from another cluster. And on a good day, I could start off wrong and actually converge in the right direction. Actually, that can happen. On the other hand, it might also not happen. Okay? So what will typically happen is that I will start with both of my centroids being from one of the clusters, right? And then what needs to happen is that one of them needs to walk over to the point where it just becomes responsible for the little thing over there. Well, unlikely that it'll happen, but a lot of the time it won't. Okay? So these are the pathologies of k-means. Any questions about any of this? Okay, very good. So, what do we do about it, right? We better have some solution to this because most problems are not like this.